What's up, future civil engineers? How you doing? I'm your instructor, Daryl J. Mendros Balbin. In this video, I will solve sample problems 8 to 10 in head losses in pipes. A concrete lined tunnel has a cross-section consisting of a rectangular part 6 meter wide and 3 meter high, surmounted by a semicircular part 6 meters in diameter. Estimate the frictional loss in the 1,600 meter long tunnel with water flowing full at 3.7 meters per second. F is equal to 0.0175. The tunnel is a rectangle 6 meter wide and 3 meter high, surmounted by a semicircle with a diameter of 6 meters. Now solving for the hydraulic radius R, that is equal to area over wetted perimeter. For the area, that is equal to the area of the semicircle plus the area of the rectangle. For the area of the semicircle, that is 1/2 area of a circle. So that is 1/2 pi r squared, wherein the radius is 1/2 of 6 meters, that is 3 meters. And for the area of the rectangle, that is 6 meters times 3 meters. Therefore, the area is equal to 32.14 square meters. And for the wetted perimeter, it is said in the problem that water is flowing full, meaning the whole perimeter of the tunnel is wetted. First, for the perimeter of the semicircle, that is 1/2 of the circumference of a circle. So that is 1/2 2 pi r, which is simply pi r, wherein the radius is 3 meters. And for the wetted perimeter of the rectangle, we have twice 3 meters plus 6 meters. Therefore, the wetted perimeter is equal to 21.42 meters. Solving for r, that is equal to 1.50 meters. And solving for d, that is 4r, which is equal to 6 meters. Now, using Darcy-Weisbach formula, we can solve for frictional head loss HF, and substituting, our F from the problem is 0.0175, the length is 1,600 meters, the diameter is 6 meters, which we just computed, and the velocity is 3.7 meters per second, and g is of course 9.81 meters per square second. Therefore, HF, or the frictional head loss, is equal to 3.26 meters. The conduit of the previous problem is used to convey water from reservoir 1 with water surface at elevation 1,525 meters through hydroturbines to another reservoir 2 with water surface at elevation 915 meters. The 1,600 meter long tunnel contains the following fittings or transitions. A. 2 long radius 45-degree bends with a coefficient of bend equal to 0.1. B. 2 wide open gate valves with a coefficient of valve equal to 0.2. C. Well-designed outlet at reservoir 1 with the coefficient of contraction equal to 0.5 an inlet at a reservoir 2 with a coefficient of enlargement equal to 1. D. Flow associated with the turbines has a loss coefficient of 0.2. What power can be delivered to the turbines in kilowatts? First, we need to solve for the head extracted by the turbine, HT, by writing the Bernoulli energy equation from water surface of reservoir 1 to reservoir 2. And this is the Bernoulli equation, wherein HF is the major or frictional head loss, which we just computed from the previous problem. HL is what we call the minor head loss, which is equal to kV squared over 2G, wherein K is the summation of all the coefficients of the fittings or transitions. And that is equal to twice 0.1 plus twice 0.2 plus 0.5 plus 1 plus 0.2. Multiply that with v squared, wherein v, or velocity, is 3.7 meters per second, over 2g, which is equal to 19.62. Solving for HL, HL is equal to 1.60 meters. Now we substitute our values into the Bernoulli equation. Since point 1 and point 2 are reservoirs, their pressure and velocity are equal to 0. H1 is the elevation of the water surface at reservoir 1, that is equal to 1,525 meters. H2, which is the elevation of the water surface at reservoir 2, that is equal to 915 meters. HF from the previous problem is 3.26 meters. HL is 1.6 meters. And now we can solve for HT. And that is equal to 605.14 meters. Now we're ready to solve for power in kilowatts, wherein Q is equal to AV. Substituting, gamma of water is 9,810 newtons per cubic meter. Discharge is equal to area times velocity, wherein from the previous problem, the area is 32.14 square meters and the velocity is 3.7 meters per second. And HT is 605.14 meters, all over 1,000. Therefore, the power is equal to 705,947.60 kilowatts. Final answer. Determine the head loss due to sudden contraction in a pipe system which abruptly changes from a diameter of 20 centimeters to 15 centimeters when carrying 60 liters per second of water. Find also the pressure difference which results from this transition. Coefficient of contraction is 0.133. The head loss due to sudden contraction, HL, is equal to Kc times v squared over 2g, wherein Kc is the coefficient of sudden contraction, v is the velocity of flow at the smaller pipe. And in this problem, let's call that v2, which is equal to q over a. The discharge is equal to 0.06 cubic meter per second, The area of the smaller pipe is pi fourths d squared, wherein the diameter is equal to 0.15 meter. Solving for V2, that is equal to 3.40 meters per second. Now we can solve for HL by substituting the values. Kc is 0.133, V is V2, which is 3.4 meters per second, and 2G is 19.62. Therefore, HL is equal to 0.0784 meter. We solved for V2. We might as well solve for V1, which is the velocity of flow at the bigger pipe. And that is equal to Q over A. This charge is still 0.06 cubic meter per second. Area of the bigger pipe is pi fourths d squared. This time, the diameter is 0.2 meter. Solving for V1, that is equal to 1.91 meters per second. Now to solve for the pressure difference, we assume that the pipe system is horizontal, and we write the Bernoulli energy equation from point 1 upstream to point 2 downstream. And this is the resulting Bernoulli equation. Substituting, P1 or pressure 1 is unknown. Gamma of water is 9.81 kilonewtons per cubic meter. Velocity 1 is 1.91 meters per second. 2G is 19.62. Since the pipe system is horizontal, that means that point 1 and point 2 are on the same elevation. Therefore, we can say that H1 is 0, H2 is 0. Pressure 2 is also unknown. Gamma of water is still 9.81. Velocity 2 is 3.40 meters per second. 2G is still 19.62. And HL is 0.0784 meters. Now solving for the pressure difference, that is P1 minus P2, that is equal to 4.73 kilopascals.